Sounds good. Okay, so the problem statement is uh, one thing that doesn't fully work today is if you want to do export and you have a model, and the model you're exporting has forward inputs or returns forward outputs that are tensor subclasses. Um, and the first place where this has really come up is in the NJT use case, where people are trying to export a model that takes in NJTs as forward inputs and slash or returns them as outputs. And in particular, there's an export flow that other people on the export team are more familiar with than me, where there's basically like AOTI regions that may or may not return NJTs, and there's some sort of like wrapper code in this like export runtime that's sort of gluing together the regions and like plumbing tensors from one output to the input of another graph. Um, and so this doesn't work in the subclass case. And the first thing that doesn't work is just that if you try to call torch.export on the model and your input is an NJT or another subclass, we will raise an error. And we can pretty easily lift it, like remove this error. And the thing that we will do if we remove the error is we will just desugar the tensor subclass. So if you have a model that you're exporting and it takes in one forward input that is an NJT, the graph that you'll get as a result of exporting it will be an FX graph that is your model's forward that will have two tensor inputs, which correspond to the values and offsets of the desugared NJT. And we can do that, but that also means that export and the corresponding like export stack and runtime will need to know about the fact that these two tensors actually came from an NJT or whatever subclass, and they have some like semantic meaning of the first tensor is the values tensor and the second is the offsets tensor. And so here's an example drawing I drew after talking to Alban yesterday with like some kind of visualization of that like AOTI flow that I was hearing about, where let's say we're exporting this F1, we're also exporting F2. F1 returns an NJT as an output, and then that output gets plumbed to the second function that we're exporting. Then in this like desugared world, there will no longer at runtime be like an NJT that flows at runtime between the two regions. And what you'll see instead is these two desugared tensors. So any questions so far?
Can I ask a
Then,
basic question?
yeah,
Why do we split the graph like this? So we're talking about inference, right?
Yeah, the concrete use case is between subnets. For example, local and merge, they are, because of the serving paradigm, they are split this way.
Is that because they run on different machines or
Yeah,
just?
they are different servers.
Okay.
Like the local is a CPU only service that is on one machine pool. The merge is more compute heavy, runs on GPU, which is another process, another machine pool.
Thanks. That is very explanatory. Um, okay.
okay.
I guess we're just gonna take as fiat from an architectural perspective that nested jagged tensors are flowing between these nets because they don't have to, right? Like you could manually unpack it and then repack it.
Like the current data container used for passing data between processes is I-value. Does I-value hold tensor subclass?
No. What I'm saying is that like in abstract, whenever I have a situation where it's like I have a bunch of tensors that I need from get from one place to another, and I don't support subclasses. If I change the first API to return to unpack the tensor subclass into a bunch of tensors, and then I change the other API to accept a bunch of things and then repack. But basically, like what is in the picture, but I just do it by hand. I don't actually need any framework support.
And in particular, that would be a modeling change. Is that
Yeah, that would
right?
be modeling change.
Like
So
take
you
a
have to change
specific
your
model.
model, right, to make it do that. And I'm okay with being told that no, this is annoying or complicated or something. But
I
I
think
do kind of just want to like check these things.
yeah, I think the original intention of using as a tensor is that the user doesn't have to do the manual pack and unpack. You just author with nested tensor, and it's a concept that you can use throughout the whole modeling, right? Because in the original model, that it's a synthetic sugar that for better authoring experience, right? It would be it would be like an imposing authoring experience change to say at this particular boundary, do the packing unpacking thing. Yeah.
Okay. I have
And
another question,
but
which is, oh, sorry, go ahead.
I have a follow-up on that. I think, Ed, in principle, what we are seeing here with Brian is the closest next step from what you were asking, which is, we don't ask the model writer to do it, but we're going to say the very first thing that happens when you enter PyTorch world is we're going to do that flatten and flatten, put that into the user model because we know where we're going to split this graph. And then the rest of the stack doesn't need to worry about it at all. And so this it's part of the very, very first thing we do on entry to the framework.
Yeah, I kind of see where we're going with the proposal. There's one more thing I want to check, which is for these graph boundaries. So sometimes like an input output represents like a public API, and like you need to conform to the API, otherwise your client can't handle it. Does this boundary between the two regions count as a public API? Or is it actually just the model can do whatever it wants? You're always going to have consistently the same thing on one side and the other side, and it's like it can be treated as a private implementation detail for export.
After flattening the at graph boundary, like it's just a bunch of like normal tensor. And at the runtime, those bunch of like tuples of normal tensors are just returned as a single I value, tuple I value, and passed downstream to other machine.
I guess what I mean is anyone like poking this I value, or is it like
So is there
encapsulated?
anyone like unpacking it and then shuffle and then send it differently kind of thing?
Yeah, I'm worrying if someone is like, oh, actually, I was expecting the I value to be set up in this particular way. Someone who's
I
not us.
I think this is a very good question. I don't know what happens in predictor. I'll check, follow up. Like, does it require unpacking the I value and then do some processing on it before sending it to the next service?
I think my kind of related question here was like my interpretation of that flow is we have these sort of like islands of subgraphs that are AOTI, and then we're in like total control of all the glue code that shuffles I values between the subgraphs. Is that accurate, or like do we have to worry about other stuff that is like user code that gets executed at runtime that's not like an AOTI region that we control the export flow of or something?
I think that essentially the glue code has to be somehow implemented in the predictor, the orchestrator.
Okay, so popping the stack here, because we don't know, we probably will just have to do the conversation twice. Once with that constraint and once without that constraint. I guess you went up with a pretty different proposal depending on which one you're in. Okay, those are all the questions I had. Brian, do you want to keep going?
Yeah, sure. So I think at least my two concrete questions based on some of the discussion in this post is, as Sherlock pointed out, like the situation here is kind of similar to how export handles PyTrees today. It's like the user returns a single output, which is a dictionary or something. And then export has some logic to return like the flattened version of that dictionary, which will now be like a list of tensors. And it also has some logic to like remember how that list can be like turned back into the dictionary. which is like pretty similar to this case with subclasses. And so like one thing we can do is in the same way that when we export, we flatten the inputs and outputs and then record that metadata to help you unflatten it. We can like give similar metadata for subclasses of like our graph now returns like 10 flat tensors, but also here's a bunch of metadata telling you like you can now reconstruct the 2 subclass outputs from these 10 plain tensors or something. One thing I was less clear of though is like at runtime we're passing these like tuples of I values around, and do we, at least in the pi tree case, are you like doing some kind of flattening and unflattening at runtime to like reconstruct the pi trees?
Yeah, like Zhengshui implemented pi tree flattening and unflattening in the runtime. Yeah.
Okay, so that might be a difference in the subclass case where like you can't literally construct the subclass or like flatten unflatten the subclass at runtime because it's like a Python construct. And so it feels like the 2 options are either have some notion of like a C++ wrap like version of the wrapper that like doesn't need to do anything, but just needs to be some kind of like holder, kind of like a pi tree. Or we just say we don't do any wrapping and unwrapping at runtime, and we like only plumb the flat things around, and we know how to plumb them in the right way. And that second thing feels more complicated in like the slicing example, or like what if you have a graph where its output gets sliced up and fed into multiple other graphs or something. Yeah.
Well, I think this example is a bit more like invented. Like we can discuss this later, like if we actually have this problem. Yeah.
Sure. And yeah, maybe this just like isn't the thing that we expect to show up.
Yeah. But going back to the metadata, the tensor plus spec thing, I think because the starting point of our whole design is like backend doesn't need to understand tensor subclass. So from runtime's perspective, after receiving let's say the overall I value, it's going to unpack it into individual tensors according to that spec. And when you returns, you package it back as a I value tuple. So I don't think runtime would need to understand this tensor subclass concept. Like it would effectively it would treat the packing and unpacking as if it is packing into a dictionary of tensors and unpacking from a dictionary of tensors. Yeah, if that makes sense.
I think that makes sense to me.
I think I definitely agree with you, Sherlock, and I think it's even one of the things we should strive for is like, let's try and not have any of the subclass metadata ever available to us after export, because in theory, as you said, we should not need them. And the compile graph should be able to handle these flat objects all the time. And we don't expect to ever need to reconstruct the subclass because we cannot anyway. So it's just going to lead to even more issues, even if we had that metadata on hand. I think the one thing that we need to agree on is what are the calling conventions, because if we change the inputs, then we need that the caller also change the input the same way. And I guess that's how the reparametrization thing for model was working so well, is because the reparametrization was a natural way to translate the calling convention by changing the state dict under the hood for us automatically. And I think if we have non-parameter subclass, we might need to do something similar as well.
Yeah, I agree with like maybe we don't want to expose the metadata for tensor subclass, but like I think a useful mental model I just came up with is, can we model nested tensor as a dictionary of tensors? The runtime today, the inference stack today accepts a dictionary of tensors. And in the nested tensor case, where you just have a dictionary, you have key, and then offset and value, and then it's a dictionary, right?
Uh,
So it goes back to the same model of like handling a dictionary of tensors.
I think the real claim from this doc that Brian wrote is we don't even want a dictionary, we want a tuple of tensors. This is the contract that we have that is simplest to get at because we already have this flatten and flatten method that exists.
I think that the only difference between dictionary of tensor and tuple of tensor is how do you identify? One is positionally identifiable, one is keyword identifiable. I'm fine with both as long as we write it in spec.
Identified from the other arguments in the inputs. Is that accurate? Or the fields in the tuple?
The field in the I'm sorry, I'm not following like your question.
So we already have these flatten and flatten methods on the subclass that already exist today that allow you to go from the subclass to a tuple of tensors and from a tuple of tensors to the subclass.
Okay.
So as long as you know that this is the tuple of like two elements that correspond to the subclass, you can reconstruct the subclass from it. There is nothing new we need to build to get that behavior. And so that's why I don't know if what you meant by a dictionary would be a dictionary to hold these two elements. The claim here is we don't even need a dictionary to hold these two elements. We already have the scaffolding needed to go from the plain tuple.
Yeah, I get what you're saying. I think in theory the information is all there. Like essentially we're saying the fields inside tensor subclass are positionally identified. The rest of the stack need to understand this. I think this is probably fine, but I would say it might be useful to make this keyword accessible because it's more readable. It's just for debuggability reason, for readability reason. Yeah, but I know this is not a compelling enough. I don't know whether it's compelling enough story reasoning. Yeah.
So I know there are questions, but very quickly, Brian, given the flatten function, we can easily generate a tuple, which is what we usually do, but we also have the keys, right? So we could as easily generate a dictionary that maps from the key that was returned by flatten to the corresponding tensor.
Yeah, and in fact, it doesn't actually return a tuple of the tensors; it returns a tuple of the attribute names.
Yeah.
So you could just easily either.
Okay, that sounds like a simple. During the unflattening, we would ignore the keys, most likely, or so. Yeah, we're not sure how much the keys will be used during the unflattening when we reconstruct the subclass, but yeah, I think that sounds like an easy extension. Yeah. Okay. Thank you. Taylor, I guess you were next.
Yeah, so maybe this is a dumb question, but is there value in maintaining it just as metadata just for the purpose of essentially backend specialization? Like I agree with your point that once you export it, you should not expect to be able to recreate the Python object. But if I hand a backend a graph and I say, here's a soup of ops versus if I say like around this box, this was MHA on an NJT. And if the backend like could do the pattern matching, brute force, but if it's much easier if it can just say like, yeah, I can pluck out this thing and run my more specialized implementation. And so I wonder if that's an argument for at least maintaining metadata about the decomposition and the provenance, if not the entire like reconstruction metadata.
Do you have an answer, Brian, or do you want me to answer?
Yeah, good.
Okay. If you can move to the image you had here. So Taylor, so the AOTI region that gets compiled is on the right side here, unflattened plus F2. So the thing that gets into the compiler works with subclass, and we do rely on the AOTI and the full compiler stack to go from to work with the subclass. It's just that instead of taking a subclass as input and outputting something, it takes the unpacked thing put that into a subclass, and then use that in the original function. So
Okay.
the compiler stack will definitely see the subclass and can do pattern matching as if nothing happened. It's just that the resulting fully compiled graph will not have a concept of subclass, but that's after it went through the whole compiler stack, because the compiler stack desugars subclasses away.
Okay. Thank you.
Ed?
I have a ancillary question for the expert folks. So let's say I have a model and I'm exporting it for AOTI, and it takes in it doesn't take in a list of tensors as input. It's a little more complicated, like a dictionary of tensors or something like that. What is the, when I look at the AOTI region after everything's compiled, what do the inputs look like for that? Or is this just not a thing? We don't pass in dicts lists of tensors.
We don't pass index. It's flattened.
It's always
What you
flattened.
get is just a list of tensors, and then together with the exported program, you have a spec called input spec, which allows you to reconstruct it back to dictionary. But like in AOTI, I don't think we use it. It's mostly for other reasons where we want to reconstruct the exported, like reconstruct the NM module from exported program.
Okay, my second question is, so you have a flat list of tensors. Is that flat list a public API from the perspective of like the predictor service? As in, like, if I reordered 2 arguments, would that be a BC breaking change? And like, there would need to be a change in predictor itself to like deal with it.
It's the ordering of the arguments is written in the exported program, the serialized exported program. So predictor or runtime would follow the ordering of the, would expect the ordering according to the exported program.
But you're saying there's some extra metadata that predictor looks at to figure out where to put the arguments?
Sorry, I'm not following like
The question. Let me think.
like okay, maybe I don't have clarity on at the predictor layer how they orchestrate multiple runtime. Like they use Sigmoid as a standalone like runtime engine. So yeah, I think
actually,
this.
so just tell me what the Sigmoid contract is, right? Like, let's say I'm building my own predictor service, and I'm like, oh, I want to use Sigmoid. Sigmoid sounds cool. Well, you know, what exactly am I getting out of Sigmoid itself?
So Sigmoid contract, like the forward function of Sigmoid, accept a list of tensors and return a list of tensor. The input lists have to match the exported program graph inputs, and the return is the same. Like basically, Sigmoid follows the contract of exported program.
Okay, so essentially what you're telling me is that Sigmoid is a runtime. I get an exported program. The exported program says it takes in this list of tensors. I need to actually pass in the same list of tensors. And what the model does, where I get the tensors from, that's outside of the contract. All Sigmoid does is, you know, offer you a, hey, you can call me with a list of tensors.
Correct. I think this is the same with AOTI. It accepts a vector of tensor, returns a vector of tensors.
Okay. And so if there is, like, following Taylor's, you know, thinking, oh, wouldn't it be good if, you know, you knew something about the structure of the inputs? If there was some, like, extra observability requirement, I guess it's possible predictor already has it, but this is sort of, like, not something we have, like, we directly offer as a thing. I don't know if that was clear or not.
I think what's clear is like from PD2 like infrastructure perspective and from sigmoid runtimes perspective, we have a contract. And I wonder if there's anyone like I wonder is there any predictor people in this room right now? But feels like we need to figure out the gap or like how to make predictor work with this. Like what I know now is like the contracts that I value, but like how does predictor manipulate the I value? I am not sure. Does predictor need to unpack the thing
Yeah,
and
because in
detect?
some sense, right, like there is something like kind of missing from our discussion here, which is like, yeah, how does predictor figure out where to like put all the inputs? Like
Yeah.
there's at least something that needs to happen here, even if it's just someone like wrote that down in some code in predictor somewhere.
Yeah.
So okay, maybe we can actually answer that question with the people we have in this meeting right now.
So, Ed, would it look something like whatever was serialized as the state dict is the beginning of the tuple, and you append to that one extra tensor that corresponds to the input, and that's what you fit in? Is that just implicitly defined in something like that based on, checkpoint plus the one input you give on top of that?
I mean, I'm not even worrying about the parameter thing. I'm assuming the parameter thing is solved in some other way, probably based on FQNs. But
Oh, because my expectation was that this would be solved by whatever is the order that state dict that was generating during export is what you have on disk,
well,
and
so
when
the
you
thing
load
about
it, it's still in.
parameters is they're special because everyone talks FQNs. So it probably is like if it is some positional order thing, then I could believe that. But I could also believe it's some FQN thing where it's like your FQN is expected to stay stable, across like the model type, and that seems fine as well. I'm talking about the input, like because like you're like there's one input. Well, yeah, maybe sometimes there's one input, but like not necessarily, right? Like maybe you have a bunch of different things you got from different data sources that you're feeding into the model, right? Like in principle, that is something you can do, which is kind of like I'm like I know there needs to be something here because like even if it's just someone hard coded it, like there is something, but it just seems like no one in this room actually knows. So unfortunately, like I don't think we can actually solve this question here.
Yeah, I can answer Brian's question about like how are the parameter addressed. They are FQN addressed. So in the Eagle model, like they are say tensor subclass parameters, and when it gets to runtime, now you need to say parameter dot offset and dot value. I think they still need to be FQN addressed, and that's why I think the dictionary idea is still probably useful.
Not the tangent, but I thought AOTI like burns in the parameters and buffers into the like SO that it generates.
Yeah, I think LTI use a different convention. It's probably positional. I don't know, but like I can tell you what.
Oh, so okay, yeah, I guess that you can use them independently. So
Wait, you said they burn it into .so?
that was my understanding. Like you don't need to pass them as inputs. They're like
There are multiple ways that LTI packaged away. In the old way, ways are included in the .so file, but I think we are trying to move away from this. I think the better way to do is LTI need to accept external weight from the runtime.
Okay, that sounds good.
Okay, I have one last question, which is the whole thing of like, how much do we hide from the runtime? Like, do we just pass a tuple of tensors, no extra info, or do we need everything, like all the other subclass metadata and all that? And just tuple sounds great, like limit knowledge of the subclass at runtime. One question about the Python API for export, which is I know there's the like you can call it dot module, and that'll like reconstruct the original and then module with the original calling convention. And you wouldn't be able to do that if we only include the tuple, because my understanding would be is you like export some model that returns an NJT, and that gives you this flat graph with no NJTs in it. And then if you want to call dot module and get this like n module back that like has the same calling convention as the original code, it would need to return an NJT, like a Python NJT as an output. And it wouldn't actually know how to do that without knowing. In order to do that, the exported program would need extra knowledge of like, for the entire flat list of tensor outputs, how do you bucket them into the various subclasses, which is the tuple thing? And then also, what is the extra like constant metadata associated with each subclass output, which we could provide. But that sounds like the thing we're sort of deciding, like how much information we want to expose.
The Python export format is different and has like more affordances. And so Angela can correct me if I'm wrong, but actually you do have a tree spec, which you use to do the PyTree flatten, unflatten. Am I correct?
Yeah.
So in fact, this extra metadata you're talking about, export is already putting that in the Python exported module.
Got it. So we have some notion of like, we drop metadata as part of the like lowering export to C++, and this extra like subclass metadata.
There's no C++ involved here. This is, I ran torch.export on a program, and then I have an exported module, which I could serialize and then deserialize, and the exported module is in Python. And I haven't done any other lowering on it. So like the most typical use case for this is in the IR for training stuff, where you're not sending it to like sigmoid or a AOT inductor based thing. You're just planning to run it in Python.
Yeah,
because you're going to do training with AutoGrid.
This opens another wall. Like,
go ahead, sorry.
Or like, does unflattening work for expert
unflattening should work. To me, this is very logical. Like for the Python ecosystem, you should have unflattening work with tensor subclasses. Because the contract for unflattening is I end up with modules that have the same contract as they did originally, right? So unless you're going to tell me, actually we're giving up on that contract.
I actually okay. The way that we get the exported program with nested tensor is with post dispatch, which would have the whole thing disfigured.
I'm talking about the pre-dispatch, wibbly wobbly training.
Yeah. But like if we are really talking about supporting training, APS training with nested tensor, then we need to make pre-dispatch work for nested tensor export. Which is not a thing yet.
I can certainly believe that.
Yeah. Sorry, I did not mean to wrap the whole conversation in that direction. I actually wasn't talking about the pre-dispatch case. I was talking about the normal post-dispatch IR case where you do get the flat graph. And then my understanding was that like ignoring pre-dispatch, only talking about the like AOT dispatch IR flavor, there's still a Python API today where you can call that module and get the original calling convention. And so in the like normal AOT dispatch case, do we still care about like faithfully unflattening back into subclasses if you call dot module on your exported program?
I guess this is a question for Angela or maybe Tuksu. Go Tux.
Why do we need to construct a subclass when you call EP to the module?
This is only me going off of the like my understanding of what dot module is supposed to do. And my understanding is basically like you export some model M, you get an exported program, you call that module, you get another N module, and that should have the same behavior as the original like user program that you exported. And so if the original user program accepts or returns subclasses, then your dot module thing should also accept or return subclasses. And maybe we're okay with dropping that like one-to-one promise for subclasses, or maybe we want to like fully like faithfully get everything to work.
So if we somehow save the metadata of subclasses on the export program, we can still unflatten it back to the original subclass, right?
I think Brian's asking a slightly different question, which is basically what contract does export give when I do a post dispatch export and then call the unflattener or like dot modules where, you know, basically from a uneducated perspective, it sounds like the contract is I am supposed to give you a module that looks like the old module, including the API. Is that actually a contract that export gives for post dispatch?
I think yes, like the calling convention of the exporter program should mimic the eager one, but I guess like for tensor subclasses, we could make an exception if it's like hard to implement.
No, we should just implement it. Is my take.
Yeah, I think it's not hard to implement. It's just like, do we want to drop metadata or do we want to keep all the metadata around?
Well, the metadata would live in the exported program, right?
Yeah.
Like there's nowhere else to put it. Except yeah, because we just agreed that, you know, the actual like non-rewrapped module just has plain tensors as inputs and outputs, right? So you just can't get it at, like you can't get it at runtime. Like it has to be encoded into the tree spec that's stored on the exported module.
This does impose an extra restriction though, which is that the metadata all needs to be serializable. Where like in theory, if we just drop the metadata, you wouldn't have that requirement.
So for export for training, we are saying we will preserve the subclasses, right? So if we say we're going to serialize export training IR, then that means the subclass we are using also needs to be serializable. So that means seems like a reasonable contract that the metadata should be serializable.
What are in the metadata?
Anything.
Like,
It depends on the
are they
subclass.
guaranteed to be
What do I need to
serializable?
serialize for NJT?
Oh, so right now, oops. These two today, ragged index.
Flag. Maybe this is fine. But like if you're telling me that like it could be anything, could be any Python object, then no. Other like all else, like you have to implement your own serializer and deserializer for your tensor subclass.
Weren't we discussing that the pre-dispatch Python aware export format would be pickled?
Okay, let me just hallucinate a bit. So if I'm doing pre-dispatch export for training IR, and there are tensor subclasses that are going to be flowing in and out of the exported product, I would just like, would I even do pickle? I don't know. I guess I could do pickle. I could also do like something a little more structured like JSON, but it does seem like a reasonable like requirement that you can't just be putting random crap in the subclass if you want it to work for pre-dispatch export. Like especially if like, you know, your program is going to be like producing these and now it's not producing them by like calling your subclass directly. It's producing them by running some compile code which produce some tensors and then repackaging them up. Like, yeah, you know, that seems reasonable to not to like
It just create a parallel universe on how we serialize tensor metadata.
Yeah.
In the current case, tensor metadata have a schema. We convert them from no dot meta value, which is a fake tensor, into that serializable tensor metadata form. Now for tensor subclass, what's the metadata? Like you have a fake
No, but hang on. But we've got this pie tree stuff, right? Do we have a schema for pie trees?
So we have a
Yes,
schema.
it's also JSON.
Okay, so like something like your subclass has to like, you know, have the schema and the JSON format there. Like that feels like okay.
Okay.
Like aesthetically.
I think the reason I wrote pickle up in my head is dtensor and the way they handle, all the specs there is through a bunch of like Python classes that they use to nicely specify how things are sharded. And these kind of things are so much easier to just pickle and forget than define a new storage format for that hierarchy of Python classes that are mostly trivial, so most likely feasible to pipe them through a new serialization format, but why?
Just
I would say that like there are other like bottlenecks for how you define what goes in the context. Like for instance, if you want your subclass to work with autograd funcs, like then they have to work. Like then there's restrictions on the actual data types that can be used. I think this is like specific to probably outer core subclasses, right? Like I don't know how many new subclasses can do the device mesh dynamo stuff and like have it be like one-off handled. So someone who's wrote at least like like a decent chunk of two subclasses, like there's already restrictions in the stack on what can go in context, which is annoying, I guess, as a subclass offer, but it's like the restriction on serializability doesn't feel so extreme.
okay, I want to return to dtensor for a second. So for dtensor to need to be serialized in this way, we would need to be in a situation where we wanted to export a program which took dtensors and returned dtensors. For a program to be like that, that means the program had already been distributed, right? So it already has some assumption about like how many nodes it's going to run on, something like that. Now, I suppose this is possible, but it seems kind of unlikely. Like, as in, it is a reasonable thing to want, but it just doesn't seem like we're actually going to like do this. Because like if I talk about training IR, right? Yeah, I'm definitely not exporting training IR with FSDP already applied, right? I'm instead exporting training IR that's single node, and then I do module swaps on the destination and then slap on my, FSDP afterwards. So like I agree that in principle, being able to export a already distributed program, yeah, sure. But I don't know. It feels like we're like very much not trying to grab that bull by the horns.
By the way, do we know how APS handle distributed training today? Are they using dtensor? Is this a real problem?
They're not using dtensor. They're using like DDP, whatever. And yeah,
Yeah.
it's
So-
post import after the IR that they're actually wrapping it.
So okay, like the training IR thing for APS training is like it's a single node forward graph.
Yeah. And one of the reasons why the module swap is so important is because the module swap is like replacing like the embedding lookups with the sharded embedding lookups, for
Yep.
example.
Okay.
And that happens after you've imported the exported program.
At the risk of throwing out fake use cases, the like we won't export FSDP ahead of time thing totally makes sense to me. I have heard about like people using dtensor in an inference setting.
Yeah, distributed inference
I
is
don't know.
another interesting one. I don't know how that should work.
Yeah, I don't know if we care about some like AOTI distributed inference thing yet, but
Yeah, that's more realistic, more of a realistic setup, like detensor in distributed inference. Yeah, I buy that.
But then the like quote unquote easy workaround is to like do what Ed said at the very beginning of like have your model take in plain inputs and outputs and then like do the detensor construction in your function or something.
You still need to pass the metadata in, right?
In the function that you're tracing, you would like construct a detensor with some given device mesh replacement. But I think what I imagine is that like in the final graph you get out, there would be no device mesh replacement anymore. And so everything would be de-sugared and burned into the graph. And so the final graph would be like plain inputs, plain outputs, and your metadata was hard coded away.
I have a question for export team. Export team doesn't have any roadmap items for distributed inference with like AOTI or anything like that, right? Is there any like murmuring about it, or also no?
No. No.
Well, like export right now is the front end with Pippi. So yeah. I guess that's the only taste of distributed.
Pippi. But Pippi's fine because Pippi you export and then you pipeline it, right? The pipelining happens after you've exported.
Yeah.
Okay. So I think this is more if like we actually decide we care, someone needs to come up with a proposal for how the heck exporting distributed programs works at all. Brian's straw man might be a good starting point, but I'm guessing there's other things to have to worry about. Yeah, like with distributed inference, your parameters are sharded from the get-go, right? So like I guess one of the first things to look at is, so what exactly is my like distributed like checkpoint loading thing for the model?
I think in my mental model, like I would say do export on every single rank. Every single rank get its own graph. In the graph, you have the sharded weight, you have the communication collective embedded in the graph. You don't have the detensor concept anymore. You have the normal tensor. Like, yeah, like of course this is assuming on a non-Python environment mindset. In a Python environment mindset, which runs distributed inference, I think it's fine to have detensor, and I don't think people would need to export it, right? Right, export is for getting out of Python. So I guess my assumption still holds. Like, if people were to use a C++ service to run distributed inference, my naive position is, you know, I don't want detensor. Give me sharded weights, give me collective in the graph, give me normal tensor.
The only problem is if they need elasticity.
Well, we can parameterize rank. Like if we're doing
Oh my
DDP
God.
and fixed mesh FSDP, it's parameterizable, but you know, nothing too crazy. Yeah.
All right. Any other final comments? Brian, does this answer the questions you have?
Yeah, I think that answered all the questions. I think at least on the like exporter program side, it's like, okay, lift the error, add all the metadata, and then from there we can figure out the details of the stuff Sherlock was saying.
All right. Thanks, everyone.
Bye bye.
Cheers.